Okay, it's midterm time. Yes, your midterm grades are in. And I really had a very bad break because of you guys. Yes, because the exam was horrible. That's why my break was bad. Yeah, the exam was horrible. Exam 2 was horrible. And I really felt bad because 12 out of the 25 multiple choice questions, meaning all the multiple choice questions that I made, came from your homework. Word for word from your homework. Like word for word without changing anything. I simply did copy and paste. I was lazy. So I was expecting you guys to do good. And I was expecting you guys to do good because when I looked at those same homework questions, you guys all scored 100% on those questions. And those are the questions represented in blue. So the blue you see over there, the same homework question you had in the exam. In the homework, everybody had 100%, like everybody. And so what I expect is that if I take the same question and I give you guys the same question in the exam, I expect everybody to also have 100% on those questions. But guess what? I have those results in red over there. Who's to blame? You guys are not serious. I'll basically say it. I will not hide my words. Yes. It means you're not doing your homework. It means you're simply copying from somewhere, I don't know, without even knowing what you're doing. You're hurting yourself, not me. I'm telling you the truth. All of you, if not 80% of you here, intend to take the MCAT. That's why you are in this class. And the MCAT, they will not get the questions from my homework to give you. The MCAT question will come from abstract, anywhere. And if you guys are unable to do the problems that you've seen before, what more of the MCAT? You need to sit up. You need to sit up. Whatever thing you were doing, you need to change it. That's a fact. When people go around and then scream that organic chemistry is difficult, it's because they don't do the work. I don't have any problem. I keep saying that. I don't have any problem with you going to check.com and getting the solution to my problem. If you need the solution manual for this homework, I will give it out to you guys. I don't care. But you should be smart enough to try to understand how did he arrive to the answer. That's what is more important. How did he arrive to the answer? Not just copying the answer. Finishing my homework on time, it doesn't matter. That's why I gave you guys an open homework. You can do it, take it several times. You have tons of millions of trials to do. I could make the homework more restrictive by giving you guys only 2 trials. But this, you have several trials, meaning that I'm giving you the opportunity to learn. Do and fail, and then when you get it, you now ask yourself, why? Not when you get it, you just say, okay, I have it, and then you abandon it. It will not help you. I'm telling you the truth, it won't. That's not why I became a teacher. I could just do like most of my colleagues do. Just come in here, just start speaking to you, pouring out stuff to you, then I turn my back and go. Then I don't care about what happened next. But that's not me. It's not my personality. It's not. So if you want to do organic chemistry, if you want to pass your MCAT, if you want to do good. By the way, a medical doctor doesn't use organic chemistry daily. So what do you think organic chemistry is in the MCAT? No medical doctor uses organic chemistry daily. But why is the organic chemistry in the MCAT? It's just to filter you guys out. That's a fact. It's the deal breaker. That's why we kick people out of the MCAT. And so if you don't want to sit up for that, everybody here knows that anatomy is important. Everybody here knows that physiology is important for a medical doctor. He uses the knowledge of anatomy and physiology day in, day out. So everybody that goes in for the MCAT is good in anatomy and physiology. But what makes the difference between you and that student is organic chemistry. That's a fact. Okay? So that's what I wanted to show you guys today, because I was really bitter. I was really bitter when I saw that. And all the part B questions came from your textbook. All. I mean all. I can open the textbook and show it to you guys. In fact, all the questions I made were questions that were within your reach. The questions that I told you where they would come from. And that was my plan, doing it purposely, so that I would come back and scream at you guys. Whatever you're doing, change it. You don't study organic chemistry on the eve of the exam. It's not a novel that you are reading. You don't study organic chemistry on the eve of the exam. You are better off studying chemistry 30 minutes every day than studying organic chemistry 8 hours before an exam. Yes. Read your textbook. I understand they call you guys generation whatsoever, iPhone or whatsoever, I don't know. Read your textbook. There's no way you will know the information if you don't read your textbook. I don't know everything. I'm just a complement to the textbook. I'm a complement to the textbook. The textbook is more detailed than I am. Read that book. It's important. That's why you pay the money for. I have free copies in my office. If you come to the office and the book is there, take the book and read it. At the end of every chapter, there are summaries of the important points. You can start by looking at the summary before you then get into the details in the chapter. Read. Not just for organic chemistry, but for everything. If you don't read, you will not be informed. That's a fact. If you don't read, you will not be informed. Some of you say the class is too early. I post the video on YouTube. Nobody cares to look at the video. When I look at the video, I see 11 views in a class of 70 when what? Less than half of the class is present at 8:30. Less than half of the class. So I expect to see about 30 views for those who are not in class. But guess what? They don't care. They don't care. I don't gain anything by posting those videos on YouTube. I don't gain anything because those videos are restricted only to the students of this class. So, you know why you are here. You know why you left your home state to come to Hampton University. So if you want to keep having fun, enjoying university life and jeopardizing your future, you are welcome to do so. The next one here is a comparison of the midterm grade and the midterm grade for last year and the one for this year. The one in red is the midterm grade for last year and the one in blue is the midterm grade for this. So the grade goes from an A plus to an F. So basically the purpose of showing you guys is to let you guys know that it's still possible to pass this class. That's basically what I want to tell you. Last year they had that distribution for the midterm and almost everybody passed, almost 85% passed. And they didn't pass the class because I curved it, no, because they worked out. They did the work after the midterm. The time is short. For your information, after the midterm, you have an exam every 2 weeks. Every 2 weeks you have an exam. So the next one is coming up in 2 weeks on the 23rd. Then exam 4 is coming up. Then exam 5 is coming up. Then your final, which is a comprehensive. So it's every 2 weeks until you guys leave. So it's time to sit up, adjust. I will not advise you guys to drop because the add and drop period ends on Friday. I will not advise to drop because I still believe that if you put in the effort, you'll be able to make it. But the choice is yours. Okay? We've only done 12% of the class so far. We still have what? About 88% of the class remaining. So even somebody with an F can potentially end up with an A in this class. Because we've only done 12%, you still have 88 points to grab. So if you have an F, it's still possible to have an A. Even if you have an F and then you end up with an 89, I will give you an A minus. I will give you an A minus. So it's possible. Okay? Great. Now, after preaching like a pastor, let's get into the real chemistry now. Chapter 8. So in chapter 8, we'll be looking at delocalized electrons. Delocalized is just another word. It's the opposite of localized. Localized means specific position. You can actually say exactly where it is. That's the meaning of localized. So delocalized means you cannot say exactly where it is. Okay, it is moving around. It's everywhere. That's the meaning of delocalized. So we'll look at delocalized electron. With those delocalized electrons, we'll definitely talk about their stability. How do delocalized electron affect stability? And we've talked about that already in this class. Delocalized, when I say delocalized, you should think about resonance. We've mentioned it in this class. And a lot of you know already what resonance does to stability, right? The more resonance, the more stable the structure is. Okay, that's the key word. And so it definitely means that the more delocalized, the more stable the structure is. So we'll see how stability and delocalization are related. We'll also talk about the pKa, which is a measure of the acidity or basicity of a compound. Okay, we'll talk about the pKa. And then we'll look at some reactions, the product of some reaction. And then we'll talk about aromaticity, what aromaticity is all about, and the electronic effect of aromaticity. And we'll most likely look at the reactions of benzene. Okay, so that's basically what chapter 8 is. Chapter 8 and 18 are very related. So that's why we'll do chapter 8 and 18 together. Okay, because they are kind of the same knowledge that is needed. So like I said, we're looking at delocalized electron. It's a competition between a localized electron and a delocalized electron. Localized electron belong to a single atom. That's basically it. You know exactly where that electron is. Okay? Or shared by atoms. That's what a localized electron is. So for example, in this first molecule we have here, which is called methylamine. This molecule is called methylamine. So we have a molecule of methylamine over here, and the set of electrons here. Oops. This set of electrons here are localized electrons because they only belong to that nitrogen. You cannot move them around. Okay, only belongs to the nitrogen. Those are localized electrons. And when you look at the other molecule, 1-propene, the pi electrons, these pi electrons here are localized between those two carbon atoms. They cannot go anywhere else. They can only stay within those two carbon atoms. So those are localized electrons. Now, compared to localized electrons, we have the delocalized electrons. Delocalized electrons are shared between 3 or more atoms. So they move around. Those are delocalized electrons. And so, for example, when we look at the acetate, the electrons on the acetate are delocalized. That's why they're represented with a dotted line. Usually the dotted line is used to represent delocalized electron, like a summary structure of delocalized electrons. Okay, and we'll look at that in a little bit more detail. Now, this chapter will focus more on the structure of benzene. Benzene is a molecule with 6 carbon and 6 hydrogen. Okay, and it follows the general formula CnH2n plus 2, which is a general formula. This is a general formula for an alkane. But if you notice, see that benzene doesn't technically follow that general formula. So benzene is not an alkane, but it is a hydrocarbon. Benzene is a hydrocarbon. Now, with the molecular formula C6H6, if you want to do the, the degree of unsaturation, if you do the degree of unsaturation, the calculation, you will notice that the answer will be 4. And you know what 4 means? 4 means you probably have 4 double bonds, or you probably have 1 ring and 3 double bonds, and you know all those kind of combinations, okay, for the degree of unsaturation. Now, with the benzene molecule, we'll have to look in detail what the structure is. Benzene forms only one monosubstituted compound. Therefore, all the hydrogens of benzene are equivalent. Okay, we'll look at that. We'll see what that means. All the hydrogens of benzene are equivalent. What we mean by equivalent, you should think about the NMR. Does that make sense? If you have equivalent hydrogens in the NMR, it means that it will give you one signal. That's the meaning of being equivalent. It gives you the same signal. It all gives you one signal. Now, there was a debate in the past of the possibility, what will the structure of benzene look like? Okay, it is a 6-carbon structure with identical hydrogen and a degree of unsaturation of 4. These are the information that we know about benzene. So we need to put this information together to propose a structure for benzene. Okay, one way you could propose the structure for benzene would be that. Because if you look at this structure, maybe let's see if that satisfies the benzene, or what we have. Degree of unsaturation 4. Remember, each triple bond provides 2 degrees of unsaturation. Okay, each triple bond provides 2 degrees of unsaturation, and then you also have this other structure that has been proposed for the structure of benzene. Okay, then we'll see which of those two will be the correct structure of benzene. Now, in the second structure, which is a hexagon with alternating single and double bond, we notice that the double bonds generally are shorter compared to the single bond that are generally longer. But that wasn't observed in the structure of benzene. In the structure of benzene, those bonds basically have exactly the same length. They had the same length, irrespective whether the bond was single or the bond was double. So that was giving us information about what the structure of benzene at the end of the day will look like. Now, in terms of determining, remember we have these two structures. We have the length, or how would they call it, the vertical or elongated structure, and the cyclic structure. We need to decide between those two structures. Which of them is the structure of benzene? So they went through a series. This is basically the history of the structure of benzene, which I don't really think I will be wasting too much time there. They went through a series of reactions, went through a series of observations. They noticed that, okay, when we have a molecule of benzene, that molecule of benzene can actually be di-substituted. Okay? Meaning that it can form a compound with 2 substituted products. But when you look at the how do they call that structure? The fake structure, I will call it that way. The fake structure actually produces 2 different compounds that are di-substituted, whereas with the real benzene molecule that wasn't observed. Okay, that's how we're proceeding by elimination, to eliminate that fake structure. And then it now came out to a conclusion that these would probably look like the structure of benzene, but there was still a debate on the bond length. If this is the structure of benzene, why then do we have some bonds that are longer and then some bonds that are shorter? And so this young guy called Cooley was the first to propose the structure of benzene, but yet he was still taking into consideration that the double bonds will be shorter and the single bonds will be longer. So that's basically what we refer to as the Kekulé proposal for the structure of benzene. It's just a proposal. That's not a true structure. That's the history of the structure of benzene. Now, that structure was used for a while. For a long time, they were using Kekulé structure until they came out with something else. Okay. Now, we know that benzene is a cyclic compound, and one of the cyclic compounds that we know is a cyclohexane. And one thing with benzene is that if you take benzene and react it with hydrogen, meaning hydrogenation, which is a form of reduction. Okay. Whenever you react something with hydrogen, we refer to that as a reduction. You've seen it in Gen Chem, right? As opposed to oxidation. Oxidation is when you react with oxygen, meaning you're adding more oxygen. Reduction, you're adding more hydrogen. So if you carry out a reduction of the benzene at very high temperature, you might end up having cyclohexane. So those are all indications of what the structure of benzene will end up being like. Okay? And now it turns out that the benzene molecule actually has delocalized electron. And you know what delocalized electron means? Electrons that are shared between 3 or more atoms. Those are delocalized electrons. So, all the carbons in the benzene ring were found to have the same length. We've talked about it. Although we have an alternation of single, double, all of them had the same length. Okay? And those lengths were longer than the normal double bond, but shorter than the normal single bond. Does that make sense? Remember that double bonds are usually shorter than single bond. But in the benzene molecule, those bonds were neither double bonds nor single bond. The length was somewhere in between. Okay? And that was explained through the effect of delocalization, because the electron was spread out between all 6 carbons. Okay? And so usually that delocalization will explain it like what is seen in structure C. So in structure C, you basically have the benzene molecule, which is a flat molecule. And that molecule is flat because all the carbon atoms on the benzene are sp2 hybridized. Does that make sense? All the carbons on the benzene are sp2 hybridized. And you know, if you are sp2 hybridized, then you are trigonal planar. Means you lie on the plane. And so the benzene molecule is a flat molecule. And the benzene molecule being flat, the question I asked you is made up of double bond in the exam. What orbitals are responsible for the formation of double bond? They are not sp2 orbitals, they are p orbitals. Does that make sense? 2p orbitals is the what that for is those are the orbitals that form pi bonds. So the benzene are flat and then the p orbital are standing perpendicular to it. And so the electrons in the p orbital interact with each other. So these electrons interact with each other. That's what gives rise to structure C. Does that make sense? That's what gives rise to structure C. And so those electrons, because they interact with each other, they keep hovering around. So there will be a cloud if we have our benzene molecule flat as this book. The p orbitals, imagine the p orbitals sticking out, up and down this way. Those are the p orbitals sticking out. And so if you have a p orbital here, it can easily interact with the one that's over here. So there will be that interaction of electron above the plane, and there will be the same interaction of electron below the plane. So those electrons will be traveling around. That's what we refer to as delocalization. And that's what actually makes the structure of benzene very stable. Okay? And you can show that using molecular electrostatic potential like this. This is just a fancy way of representing C. Okay? The red region on this diagram actually represents electron rich, and then the green region technically represents electron poor. Okay? And so, in order to represent that in 2 dimensions, in order to represent structure C in 2 dimensions, the way we usually represent it is drawing a hexagon with a circle in the middle. Okay? And that circle in the middle simply shows the pi electrons that are being delocalized all over the 6 carbons of that hexagon. It can be a solid line circle or it can be a broken line. Okay? That all depends on you. That's just a summary structure of the benzene molecule. This is the first and the last time I will use this kind of structure in this class, okay? Just for your information. The best way of representing benzene is by looking at the detailed structure. Okay? It is a resonance contributor. We can represent benzene this way or we can represent benzene that way. I hope you guys notice the difference between those 2 structures. In structure A, for example, the double bond is between carbon 1 and 2. And then in structure B now, between carbon 1 and 2, you have a single bond. So those bonds have virtually changed position. Do you see that? I want you to observe and see that. That the bonds have virtually changed position. For example, this bond here moved to that position. At the same time, this guy moved to this position. At the same time, this moved to that position. That's what gives rise to structure B. The movement of those bonds, changing those positions. It gives rise to structure B. And so in real life, that's what is happening in the benzene molecule. Those bonds change this position so fast that sometimes we just decide to represent this. That's what we call a hybrid structure. You know what a hybrid means, okay? Hybrid, it means a resultant of 2 or more things. That's what a hybrid is. So all of you guys here are hybrid of your mom and your dad, right? You're a hybrid of your parents. So that's what it is. And so we'll be looking more at structure A and B. That's why we should be familiar with structure A and B. A or B, whichever one you choose. Those are the 2 structures we'll be looking in this class more keenly. Okay. This is just a cartoon representation of what a hybrid structure is. I don't know if a unicorn actually exists, but if you mix a unicorn with a dragon, then you will form a rhinoceros. Maybe that's true. That's how a rhinoceros actually came to life. You know, because chemistry explains everything, you know. That's why you don't see unicorns and dragons again, because they have been transformed to rhinoceros. That can be a good story for my children. Yeah. Do you know why a unicorn and a dragon doesn't exist? because they decided to couple together, and then it gave rise to a rhinoceros. So that's a hybrid structure. That's a hybrid structure. Any question? Okay. Let's talk about delocalized electrons. Do we have any questions for now? No? That's great. So delocalized electrons and resonance. Now, the delocalized electron actually comes from the p orbitals of one atom that overlaps with the p orbitals of an adjacent atom. You remember like what I showed in the benzene. If this is our fake benzene, here you have this p orbital hanging there, you have this p orbital hanging there. If the electron jumps from this p orbital to this other p orbital, that's basically what delocalization is. Does that make sense? So electron jumping from one p orbital to the other. So you keep moving around from p orbitals to p orbital. That's what delocalization is, and that's what resonance is all about. So your job will be able to show that resonance. Okay? You'll be able to show that resonance. So this is one of the resonance structure, which is represented as a resonance contributor, and this is another resonance structure over here. If you notice, the double bond was initially between this oxygen and that nitrogen. And then you now notice that the double bond has virtually changed position, and now it's between this other oxygen here and that other nitrogen. So you have that change of position. And now in order to come out with a consensus between those two structures, we now have the hybrid structure over there. Does that make sense? We have the hybrid structure over there. Now, how to draw resonance contributor? You guys will read those rules. I will just practice those rules here, but you will read them in detail. Now, usually the way I teach how to draw resonance contributor to my students, I think I've done it in this class already. I use the formula x equals y minus z star. We've done this in this class already, right? Yes. So that's usually what I do in order to determine my different resonance structures. I'm so sorry. So that's what I usually do in order to determine those resonance structures. X equals y minus z star. The star could be a positive charge, it could be a negative charge, it could be a pair of electrons, or it could be a single electron. Okay? So, the star could be positive, it could be negative, it could be those two, or it could be just one electron. That's what the star is. And so, the movement of my electron, depending on what the star is, your resonance contributor now will be x minus y equals z, and then the star goes to the x now. So usually those are the two resonance structures you will always have. And so for this example, you need to identify which one is x, which one is y, which one is z. And so in this case, the first oxygen is my x, the nitrogen is the y, and the second oxygen is a z. And you see there's a double bond between x and y. Does that make sense? And so in order to do my resonance here, the electrons from the star move here, and then this electron moves over there. Those are the arrows representing my resonance. So the electrons, my star in this case is a negative charge. My star in this case is a negative charge. So the negative charge now will migrate between y and z, and then the electrons will now move between y and x and then goes to x. So that's what we now have as a resulting structure. This stays my x, this stays my y, and then this one stays z. But in this case, the star now moved to the x. Does that make sense? That's how I draw my resonance contributor. The challenge here is always to be able to determine what that XYZ component is. That's where the challenge is. The ability to determine the XYZ component. And it doesn't only stop with 2 resonance contributors. There are some molecules that can give you 5 resonance contributors. Some can give you 3 resonance contributors. So you will do the same thing. You keep repeating the process until you come back to your original structure. Does that make sense? You keep repeating the process until you come back to the original structure. So that's how you draw resonance structure. That's how you do it. And so I will not read these rules for you. You guys should be able to read the rules, okay? If you read the rules, it just help you teach you guys how to draw those different resonance structure. I will simply have to do more examples here. Now, this is another example of drawing resonance contributors here. So we have this molecule over here. Like I said, the challenge is to identify your X, Y, Z in this system. And in this system, this will be my X, that will be my Y, and that's my Z. And the star is the positive charge. Okay, take note. My star now is a positive charge in this case. Like I said, the arrow, the direction of the arrow is always from electron rich to electron deficient. And so you will notice that the way we push the arrows here is a little bit different from what we did before. You see, from here, the arrow started from Z. In this first example, the arrow started from Z to go downward because Z was the one with the negative charge. Arrow starts from the negative and then ends up somewhere else. Does that make sense? But in this other case, where our star is a positive charge, the direction of the arrow is a little bit different. In this case, the electron rich is the double bond, so that's where the arrow should start. So the arrow starts from the double bond, electron rich, and then sinks on Z, which is the electron deficient. And so basically what you've done, you move your electrons. This is X, that's Y, and that's Z. Now the star has migrated to the X. Do you see that? That will be the resonance contributor for that one. Are we okay with that? Okay, with moving those electrons. And so because the sp3 carbons are already saturated, they have attained the octet, electrons cannot move to the sp3 carbon. So electrons can only move between sp2 atoms. Only atoms that are connected by sp2 bonds. Okay? And so you will never have this kind of resonance structure. You will never have that kind of resonance structure. And so there are more examples. Remember I said, you will keep doing that. You will be doing that until you can no longer do it. You will do that until you come back to the original structure. Same example here. In this other example, this is my X, that's my Y, and that's my Z. Does that make sense? And so the electron now will move from here to here. When I do that, I now end up having this resonance contributor. This stays my X, that stays my Y, and that stays my Z. But what do? I observe the structure and I notice that I have another X, I have another Y, and I have another Z. Do you see that? For observing the structure, I notice another X, another Y, another Z. So I can perform another resonance structure on that one. And so if you perform that other resonance structure, you end up having this one. Does that make sense? End up having this one. And so you can now come out with a hybrid structure. That will be the hybrid structure. In your hybrid structure now, take note, you are distributing the electron among 1, 2, 3, 4, 5 atoms. Because those were the 5 atoms that were involved in the push. These atoms here. Those were the 5 atoms involved in the push. And the easier way is always to identify them. If you have a continuation of sp2 carbons, if you have a succession of sp2 carbons, chances are that those sp2 carbons will all be part of the resonance structure. Does that make sense? If you have 1, 2, 3, 4, or 1, 2, 3 sp2 carbon aligned together, then they can perform a resonance structure. If you have 5 sp2 carbons aligned together, then they can perform a resonance structure. If you have 7 sp2 carbons straight with each other, they can perform resonance structures. Does that make sense? So take note, if you have a succession of sp2 carbon, yes, But if those sp2 carbons are separated by an sp3, then the resonance will break at the level of that sp3. Are we good with that? So if I ask you to draw a hybrid, the hybrid now will just be a dotted line that cut across all the sp2 carbons that are involved in the formation of that resonance structure. That's what your hybrid will be. And so we have more examples of moving things around. We have more examples of moving things around, more and more examples. Okay. And so here again, same stuff. We have our X, we have our Y, we have our Z, and then you can move it around. If you move it around, you will see have your X, you will have your Y, and you will have your Z. Same direction, same movement that we've done. But then, look at this one. This other structure here cannot undergo resonance, okay? Because this carbon here is not sp2. And so that's what I mean, like if you have an sp3 between the sp2 guys, it will break that resonance channel. It will break the resonance channel. I'm talking about sp3 carbon. I'm not saying an sp3 atom. Take note, okay? I'm talking about an sp3 carbon, not an sp3 atom. What I mean is this. What is the hybridization of this nitrogen here? Oh, sorry. This hydrogen here is sp3. Yet there's resonance. Does that make sense? This nitrogen here is sp3, but there is resonance because of those lone pair of electrons. That lone pair of electrons is in the p orbital. This lone pair of electrons is in the p orbital. And remember that resonance has to do with electrons moving from one p orbital to the other. So long as you have a p orbital with electrons in there, chances are that you can do resonance. That's why nitrogen here can do resonance. That's why oxygen, if oxygen is sp3, yes, oxygen can do resonance, even in the sp3 state. But carbon in the sp3 cannot do resonance. Yes, sir. Electrons in the p orbital, then you can do resonance. But carbon with an sp3 cannot, because the carbon with an sp3 doesn't have electron in the p orbital. All the orbitals of carbon are used for bonding. They are all sp3 orbitals, and they are all used for bonding. Does that make sense with resonance? Okay. So the challenge here is also to be able to draw the hybrid. And so in this case, my hybrid would be between those three atoms, because those are the three atoms that are involved in the formation, in that resonance structure or resonance contributor. And so you can now keep moving them around. You've been doing that several times. You can keep moving them around. Okay? You can keep moving all those structures around. What is true for sp2 is also true for sp, meaning that carbons that are sp bonded can undergo resonance. Why? Why would those carbons undergo resonance? Why would sp, carbon with the sp hybridization, undergo resonance? How many p orbitals are there? There are two p orbitals. Does that make sense? There are two p orbitals, so it meets the minimum requirement for resonance. Remember that to do resonance, you need to have a p orbital. sp2 will only have one p orbital, and then the sp will have two orbitals. So because of those two orbitals, it can easily undergo resonance. Does that make sense? So the sp carbon can also undergo resonance. And you will do the resonance exactly the same way like we used to do. And you can come out with a hybrid structure over here. And you notice that the hybrid structure, all the atoms there are involved. And that's simply because this guy here, all the atoms here are involved because this carbon is sp2 hybridized. Okay, this other carbon here is sp2 hybridized. This other carbon here is sp hybridized. What about this nitrogen? What is the hybridization of that nitrogen, guys? Tell me. And that nitrogen is sp hybridized. So they all meet the requirement for resonance. Okay, so that's why when you will now draw the resonance hybrid, it will cut across all the atoms. You will see the dotted line will cut across all the atoms. Yes.
So it isn't necessarily like
Yes.
So on that structure right there, what is like is the Z star, is it the SP plus?
That SP carbon is a Z star. Yeah. So delocalized electrons. Why do we study all these things, by the way? Delocalization is very important in understanding protein structures. Okay? Because in the protein structure, you have a specific type of bond which is referred to as a peptide bond. And a peptide bond is a bond formed between a carbon double bond oxygen and a nitrogen. That's an example of what we refer to an amide. We'll talk about that more in the future. Okay? If you look at that amide bond, you can easily see the XYZ component in there. Okay? You can easily see that XYZ component. And if you have that XYZ component, it means that you can easily form resonance structures. Does that make sense with everyone? If you see that XYZ component, it means you can easily form resonance structure. The peptide bond is the basis for the protein. It's the basis for the formation of the protein structure. And you all know how important proteins are. That's where all proteins, that's the building block, right? And so those enzymes and all those protein molecules are made up of those peptide bonds. And what makes those protein structures stable, what stabilizes those protein structures, is because the peptide bond can easily resonate. They can form resonance. And remember, the more resonance you form, the more stable. And so because those peptide bond can resonate, then your protein structure becomes stable. Does that make sense? So that's the basis of life. That's how important organic chemistry comes in now. That's how important resonance can be to us. Okay. Now, we will be able to now use resonance to determine stability. Should be able to use resonance to determine stability. I haven't prepared I wanted to give a, what is it? How do we call it? QR question. But I don't have one here. So I will just get one from the book and we'll do a practice. I'll just pull a question straight from the book so that we can practice. Problem number 4. Problem number 4 from the textbook. We have two molecules. Structure A and structure B. They are asking us the question, between A and B, which one is more stable? Between A and B, which one is more stable? Do everyone go with A? Okay, I go with A, right? Why is A more stable? Why is A more stable? What's Adia, by the way? It's not A. I was about to call her name, so I did call her. So do we know why A is more stable? I will not take that reason. I will not take that one. Look at the two structure, A and B. Which one is more stable, guys? Do you see that? And over here we also have X, Y, and Z over there. So question, which one is more stable? Think about your resonance structure and then think about what we have done in class. I will go with B. But I want you guys to be able to tell me why B. Think about the resonance structure. Yes, Diana.
Does it have anything to do with the bottom side of my brain fluid circulation?
With not tertiary carbon.
Or secondary?
Yeah, I think yes, Brownie.
Is it because it has one deposit?
No.
Is it because it's an sp3 family?
It has to do with the positive charge. Draw out the two resonance structure, please. Go ahead. Draw out the resonance structure for A and draw out the resonance structure for B. And look at those resonance structures. Draw out the resonance structures and look at them. That's what I want you guys to do. You know how to draw. We'll practice how to draw resonance structures. So practice with this one. Practice to draw the resonance structures here. Let's see. Most of it is B, but look at the resonance structures. No. Remember, conjugation has to do with double single, double simple thing. And we'll talk about that in the future, how conjugation affects the class. While you guys are doing it, I will also do it here on my own. So those are the two resonance structures. Okay. So this is, I'll call this one A prime and I will call this one B prime. Yes, bro. Say that again. Hallelujah. Do you see it now? Can you see? Look at structure B prime. Compare B prime with A prime. Do you see the difference now? With A, if you look at A, both resonance structure, whether structure A or structure A prime, the positive charge is always on the primary carbon. Does that make sense? The positive charge is always on the primary carbon. But when you look at B, in B prime, the positive charge is on the secondary carbon, making it more stable. Does that make sense? So that's why B is overall a more stable structure than A. Does that make sense for everyone? Is that okay, guys? That's what I want you guys to think about it. Now, look at B and B prime. Again, I can now ask you, which one is a greater resonance contributor between B and B prime? Between B and B prime, this is my B and that's the B prime. Between both, which one is the greater contributor? B prime. Does that make sense? And the reason is the same. Because B prime, the positive charge, is on the secondary carbon. Does that make sense? B prime, the positive charge is on a secondary carbon. That's how we make those differences. That's how we compare them. That's how we compare them. And so you guys can try this again on your own. C and D, which one is more stable between C and D? And to answer it, you have to draw their resonance structure. When you now draw their resonance structure, you now look at them and then make a decision. C and D, which one is more stable? We need to be able to draw their resonance contributor. Is that okay? That's the first task. Let's do it together. I'm deleting this B and B prime because we're done with them. So let's look at C. I want to draw the resonance contributor. The electrons here. So the first thing I want you guys to look at, first thing I want to pay attention. This is sp2, 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 sp2. So all the atoms there are sp2. So they will all take part in that resonance structure. Does that make sense? They are all sp2 and they are all connected together. So all of them will be part of that resonance structure. That's the first thing I want you guys to take note. So in this case now, the arrow will move from here to here and from here to here. Think of those arrows as electron moving. Think of those arrows as electron moving. So if I draw the resulting structure over here, I have a CH3, a carbon. Now, between this carbon double bond oxygen here, this carbon double bond oxygen becomes a single bond. I want you guys to see that. Because I took the electrons here and then gave it to the oxygen. So this becomes a single bond and then the oxygen ends up with an extra electron or an extra pair of electrons. Does that make sense? Because this is the extra pair of electron moving to the oxygen. That's what the arrow means. So this becomes a single bond with an oxygen having an extra pair of electron, negative charge over there. With the oxygen, the extra pair of electron. Now, the remaining structure over here, this is a carbon. This bond becomes a double bond. And you can see why it becomes a double bond. It becomes a double bond because I'm taking these electrons and then I'm creating a double bond here. Is that okay? And at the same time, this bond now becomes a single bond. So that becomes a double bond, and the other one becomes a single bond. A single bond with a positive charge. Why do I put a positive charge? Initially, the electrons here were shared between these two carbons. But I took the electrons and now shared between these two other carbons. So this carbon becomes deficient in electrons. Does that make sense? This becomes deficient in electrons. That's why I have a positive charge there. So that would be the resonance structure for C. I want you guys to draw the resonance structure for D. And then tell me which one is more stable now. Sorry, this is a CH2 here. I want you guys to draw the resonance structure for D and tell me which one is more stable now. Yeah, because those pair of electron comes in and makes that oxygen negative. That's why I just show a negative there. If you put, then that oxygen will actually have 3 pairs of electrons because originally it has 2. And so you are bringing the 3rd pair. So if you want to show, you have to show all those 3 pairs of electrons. Yes. Say that again. Because it also has 3 bonds, 3 sigma bonds. There's 1 sigma bond, 1 sigma bond, 1 sigma bond. Okay. If you are sp2, sp2, s1p2, 1 plus 2, 3 sigma bond. That's the way I always do it for carbons. That's the way I always know. Okay. Yes.
So what is the XYZ star between the 2 types?
You know there are always good exceptions. XYZ, it works when you have 3 sp2 carbons aligned together. But here you have 4 aligned together, so XYZ will not work. Okay, XYZ is only when you have 3. So with D, guys, were you guys able to draw down the resonance structure? So which one is more stable? Why? Because the secondary carbocation in D. Does that make sense? Because this carbon here now becomes positive. If you don't know how to do it, do it. Okay? This carbon now becomes positive, and that positive will be on the secondary compared to having a positive on a primary. Does that make sense? That's how resonance also can help you determine stability. Is that okay? That's basically how resonance can also help you determine stability. And you have more practice exercise. You know what? It won't kill you. You can leave my class today and then take the next 30 minutes of your day sometime in the day and do C and D. If you do it today, you will know it. But if you keep it to do it tomorrow, you will forget. That's the way I want you guys to learn. If you do it sometimes today, you can say, okay, around 3 o'clock, I will do C. Then before I go to bed, I will do D. Then you will never forget it. But if you leave it and then think about doing it tomorrow or after tomorrow, you will forget. And then you will say organic chemistry is difficult. I still have 6 minutes, right? Does that make sense? So go over and finish it up. Finish it up. A has a greater predicted stability than B. A has a greater predicted stability than B. So here we have 2 resonance structures between A and B. And we need to understand why A is a better predicted resonance structure than B. Why do you think A is better than B? If you look at that, remember, we're now thinking about the concept of what? Formal charges. You remember about the concept of formal charges and stability? In formal charge, when we did that in Chem 301, formal charges we said electronegative atom. What kind of charge do they prefer to have? They prefer to have a negative charge. Does that make sense? That's what we said in 301 when we're doing formal charges. If you are electronegative like oxygen and nitrogen, you prefer to have a negative charge. In fact, the perfection is being neutral. Everybody wants to be neutral. Everybody wants to have a formal charge of 0. And the closer you are to 0, the better. That's the first thing I want you guys to remember. The closer you are to 0, the more stable. But then, electronegative atoms, negative, it means they would rather prefer to be negative than positive. Does that make sense? So atoms like oxygen and nitrogen would rather prefer, if they cannot be neutral, if they cannot be 0, then they would rather prefer to be negative. Does that make sense? As opposed to electropositive atoms. Electropositive atoms, if they cannot be if they cannot be neutral, then they would rather prefer to be positive. And so when you look at structure A and B, that's what will help you distinguish which one is more stable? If you look at B, you notice that, if you look at A, let's start with A. If you look at A, you notice that both oxygens have a formal charge of 0. They all have formal charges of 0. Does that make sense? And having a formal charge of 0 is what they want. But when you look at structure B, there is an oxygen there with a formal charge of +1. And oxygen doesn't like that. Does that make sense? Oxygen doesn't like to have a positive charge. He doesn't. So B will be a bad resonance contributor. Well, not the bad, will not be the more stable, will not be a greater resonance contributor. So A will be more stable than B will be. Does that make sense? Yes.
So if we just had like a negative charge, the resonance structure, it would still be that A is negative.
Yes, because remember, everyone prefers to be neutral. Now, if you cannot be neutral, then the electronegative prefer to be negative. Does that make sense? Everyone prefers to be neutral. C and D, which one is more stable? They have the same stability. Does that make sense? C and D have the same stability, and you can guess why. Because they're basically the same stuff. Okay? In structure C, there is an oxygen with a neutral charge and there is an oxygen with a negative charge. In structure D, one with a neutral, or one with a negative and one with a neutral. So the stability should be the same. Does that make sense? E and F, which one is more stable? We've talked about it already. This is E and F. Which one is more stable? E is more stable because everybody here will have a 0 formal charge. Everybody has a 0 formal charge. Whereas with F, there are some people whose formal charges are not 0. Remember I said it. Everybody prefers to have a formal charge of 0. That's the preference by default. Another way you can explain it is using the octet rule. If you look at F, this carbon here does not observe the octet rule. Is that okay? Those are differences. G and H, you know the answer. G is more stable and you know why. Okay? J and I, which one is more stable between J and I? I will go with J, right? J is better because here, look at this carbon. Carbon is having a negative charge. Carbon cannot be negative when oxygen is present. Does that make sense? Carbon cannot be negative when oxygen is present. If oxygen is present, then oxygen will prefer to be negative. Does that make sense? That's the way I want you guys to think about it. Blah, 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 blah. You have a summary of those things there.